We are now going to look at another example where we use enthalpies of formation to calculate the enthalpy change for an overall reaction. This example once again comes from outside the textbook, but the OpenStax textbook has a very similar example where you use delta HFs to calculate delta H naught reaction. In this example, we're asked once again to calculate the overall enthalpy change, delta H naught, for a balanced chemical equation which describes the synthesis of so-called quicklime, calcium oxide, from limestone calcium carbonate. Our balanced chemical equation, once again, is 1 mole of calcium carbonate in the solid phase decomposes under heating to give us 1 mole of calcium oxide in the solid phase and 1 mole of carbon dioxide, CO2, in the gas phase. We're asked to calculate delta H naught reaction, so the enthalpy change under standard conditions for this chemical reaction. This time I've gone ahead and given you the enthalpies of formation for the reactants and products, which have been pulled from Appendix G in the OpenStax textbook up front in the problem. And again, the information given is going to inform the most efficient strategy for calculating the enthalpy change of reaction. So if we're given a balanced chemical equation and we're given enthalpies of formation, the move is to use the enthalpies of formation for the products and the enthalpies of formation for the reactants and compare the difference between the two to calculate the enthalpy change for the overall reaction. So our general strategy will be to add up the enthalpies of formation for the products, and from that we subtract the enthalpy of formation for the reactants to give us the overall enthalpy change for the reaction. From Appendix G, we see that the enthalpy of formation for calcium carbonate is negative 1207.6 kilojoules. For calcium oxide, delta H naught F is negative 634.9 kilojoules. And for carbon dioxide, delta H naught F is negative 393.5 kilojoules. We will take the enthalpies of formation for the products, and from that we will subtract the enthalpy of formation of the reactants to get the overall enthalpy change for the reaction. And remember, it's very important in these calculations that you get the little details right. The simple math associated with these problems may seem like a nice bit of relief from the calorimetry problems that we talked about earlier in the chapter. But since the math is simple, it's important to nail all the little details correctly. Make sure that you're subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products, and make sure you're taking the stoichiometric coefficients into account. In this problem, because the reaction occurs in a 1:1:1 molar ratio, we don't have any stoichiometric coefficients to multiply the enthalpies of formation when we do our calculations, but that won't always be the case. Our enthalpy of reaction is calculated as the sum of the enthalpy of formation for calcium oxide plus the sum of the enthalpy of formation for carbon dioxide, and from that we subtract the enthalpy of formation for calcium carbonate. The enthalpy of the reaction, the enthalpy change for the overall reaction is therefore 1 mole times negative 634.9 kilojoules per mole plus 1 mole times negative 393.5 kilojoules per mole. We calculate that number, and from that we subtract 1 times negative 1207.6 kilojoules per mole. When we take this difference, the overall enthalpy change is positive 179.2 kilojoules. Therefore, the overall reaction is endothermic, and the overall enthalpy change for the reaction is 179.2 kilojoules per mole of calcium carbonate that decomposes.